Okay folks, we're going to try recording a video today where I work out a few of the problems from the AP Calculus BC summer packet. So let's get started. We're going to start with the first problem, which asks us to evaluate the limit as x approaches 4 of the quotient 4 minus x divided by the square root of x minus 2. Now, as always, the very first thing we should try here is direct substitution. I'm going to write this out in probably a little bit more detail than you might do. You would probably do this step using mental math. So I'm taking the limit of the numerator and the denominator separately. Now, 4 minus x is linear, so the limit of 4 minus x we can calculate by direct substitution. It's just 4 minus 4, which is 0. Same thing works here. The limit as x approaches 4 of the square root of x minus 2 is the square root of 4 minus 2, which is also 0. This amount of work is not always required, particularly for multiple choice questions, but if we're working a limit problem on the free response portion of the exam, we need to make sure we check the limit of the numerator and the limit of the denominator as a separate calculation, because this shows us that we have a limit of the form 0 over 0. It's perfectly okay to just informally use this notation to indicate that the numerator and denominator individually both approach 0. So that means because we have an indeterminate form of 0 over 0, we're going to use L'Hopital's rule. So we're still calculating the limit as x approaches 4, but I'm going to take the derivative of the numerator and the denominator separately. Of course, the derivative of 4 minus x is just going to be -1, the coefficient of x. The derivative of the square root of x minus 2, well, that's just going to be the derivative of root x. Well, if you remember, root x is x to the 1/2. So when we take its derivative, that would be 1/2 x to the -1/2, otherwise known as 1 over 2, that's the 1/2, divided by the square root of x, because x to the 1/2 power is the square root. The negative exponent throws it down into the denominator. So that becomes the denominator of my new problem here. We have 1 over 2 square root x. That is a plus sign, not a minus sign. Okay, so let's see if we can't simplify this fraction before we try to evaluate. We've got a compound fraction. We're dividing by a fraction, so let's write it as multiplication instead by flipping the fraction. So we're going to multiply by the reciprocal of the denominator, and now we can see that we can evaluate this limit by direct substitution, because the square root of x is a continuous function, so I can just plug in. This is -1 times 2 times the square root of 4. So we have 2 times root is 4, so we have -4, which I believe is answer choice B. Okay, the next problem I'm going to look at is quite a bit more challenging than number 1. Let's going to go ahead and take a look at problem number 6. Problem 6 says find the limit as a approaches 0. So we're going to be looking at a limit as a approaches 0 of the y-intercept of the line normal to the parabola y equals x squared at the point a comma a squared. So let's just translate that. Let's see. So it's the limit as a approaches 0 of the y-intercept of y equals x squared. Well, and they go ahead and say at the point a comma a squared. Well, let's make sure we understand what that means graphically. We all know what y equals x squared looks like, so let's sketch out the parabola passing through the origin. Let me see if I can do better. Much better. Okay, so when they say the point a comma a squared, what they mean is, okay, let's pick an arbitrary point on the curve. We're going to label its x coordinate as a, And because the graph is y equals x squared, the y coordinate is going to be a squared. So we're looking at a normal line. So I've left this out. It's the y-intercept of the normal line of, left that part out. It's the y-intercept of the normal line. Now what's a normal line? Well, we know what a tangent line is. I can draw the tangent line over here at the point a comma a squared. And the normal line is very much like the tangent line, except rather than being parallel to the graph, it's perpendicular. So the normal line, the one that we want, passes through a comma a squared. So this is our normal line, and it is perpendicular to the tangent line. So this graph gives us most of what we're looking for. So what we're looking for here is something about the y-intercept. Well, we can see the y-intercept on this graph. The y-intercept is this point right here, where the tangent line crosses the y-axis. Now, this is where it gets a little tricky in terms of visualizing it, because we want to know what the limit of that y-intercept is as a approaches 0. So visualize sliding the point of tangency down towards 0, 0 on the origin. Where does the y-intercept end up? Does it hit the origin? Maybe it goes to infinity. Maybe it hits some point in between. Think about that for a second. Pause the video and think, where do you predict the y-intercept is going to end up as a approaches 0? Okay, well, let's see if we can't construct the equation of that normal line, and then we kind of can play around with it and go from there. All right, so we need, for the normal line, just like for the tangent line, we need two pieces of information. We need a slope, and we need a point. Well, the point we already know. It's a comma a squared. That's the same as the point of tangency. The slope, however, we don't know. But we do know the slope of the curve. We know that this slope here is going to be related to the derivative of x squared. So we know the slope of the tangent line is the derivative of x squared. Well, we all know that is 2x. So the slope of y equals x squared at a comma a squared is always going to be 2a. Well, if we want the perpendicular slope, we have to remember, we have to go back to geometry for a moment and think, okay, how are perpendicular lines' slopes related? As it turns out, two lines that are perpendicular to one another have negative reciprocal slopes. So I'm going to take the slope of 2a, I'm going to think of that as a fraction with a denominator of 1. To get my normal slope, or my perpendicular slope, I'm going to flip that fraction over, write 1 over 2a, and then I'm going to change the sign. So flip the fraction, change the sign, that gives me the slope of the normal line, or the slope of the perpendicular line. So now, we can write the equation of the normal line the same way we write the equation of any other line. Y equals the slope, m, times x minus the x value plus the y value. So x1 comma y1 is any point on the line. In this case, the point we have is a is x and y is a squared. So that's our a comma a squared for our point x1, y1. Our slope m is our normal slope, our perpendicular slope of negative 1 over 2a. Now we've got to think a little bit about what we're going to do with this. We're looking for the y-intercept of this line. So now we go back to algebra, pull up a basic from algebra, and then the y-intercept will occur when x equals what? Well, we know that that y-intercept is going to occur when x is equal to 0. So we take our equation y equals negative 1 over 2a times x minus a, but instead of x we sub in 0 plus a squared. Okay, that can then be simplified. Let's see here. 0 minus a is the same as negative a, and now we have negative 1 over 2a times negative a plus a squared. Well, when we multiply these two fractions together, we're going to think of this as negative a as having a denominator of 1. When we multiply the fractions together, the a's are actually going to cancel, and so are the negatives. So this ends up being positive 1/2 plus a squared. Notice that that doesn't have any x's in it anymore. That the y-intercept here does not depend upon the value of a. So this point right here that we marked with the open circle, that point doesn't move. That no matter where we are, a comma a squared on the curve, the normal line always passes through that same point. It is the point that has the y-coordinate of 1/2 plus a squared. So we can actually go back to our diagram here and label that. This point right here, its y-coordinate is 1/2 plus a squared. Now it does depend upon a, so I said it doesn't move. That's not quite right. It does move. As a approaches 0, we want to know, so the limit as a approaches 0, remember a is our x-coordinate, so we want to look at the limit as a approaches 0 of 1/2 plus a squared, because the x-coordinate is a, and x has to approach 0. That's what they ask us to do in this problem. So as a approaches 0, well, that's easy. We're only left with the 1/2. So in our picture, as the point a, comma a squared slides along the curve towards a equals 0 here at the origin, the y-intercept is going to approach a point right here at y equals 1/2. Okay, and that is problem number 6. We're about 12-13 minutes into the video, so I think that's where I'm going to stop this one.